This lab consisted of me dropping a whiteboard eraser and analyzing the effects of Newton's first and second law on it. It was first affected by only gravity and then both by gravity and drag force. The motion was analyzed in Tracker and then modeled in VIDLE. The computational model and then the experimental models were then compared to understand that there is a net force acting on the system as it reached terminal velocity. Newton's first law states F equals ma, that an object in a uniform motion will stay in that uniform motion unless acted upon by another force. In this lab, the eraser does not stay in a uniform motion because of its gravity and drag forces. We also have Newton's second law, or the momentum principle, delta P equals F net delta T. You can derive that into V final equals V initial plus F net over M delta T. Here the net force is not zero. We know this because there isn't a constant velocity. There's at least one agent in the surroundings affecting the system. Again, these are the weight forces and the drag forces. The object will accelerate at a rate inversely proportional to its mass. The video recorded at 30 frames per second and a height of the student shown as 1.714 meters. This was used to calibrate the length scales in the video. The coordinate system was chosen with the origin at the center of the paper just before the whiteboard eraser was dropped. The y-axis was aligned such that the object moved in the negative y direction as it fell. Note that because the camera was tilted when the video was made, we needed to tilt the coordinate system slightly to align the y-axis with the direction of motion. The center of mass for the object was marked by eyeing each frame. In many frames, the object was blurred, and we marked the center of the blur as our best estimate for the center of mass, or the average position of the object. The points are plotted here in the right, and the graphs turned out to be curved, showing acceleration. I took data here, and I took the initial position, as well as the final time, to create a model. From the analysis, I obtained the position of the object as a function of time shown in brown squares in a plot generated using Excel. The motion of the falling object is observed for a total duration of 0.766 seconds. At the beginning of my video, where I started my analysis, the object is located at the origin by my choice of coordinate system, and the object is at rest, moving with zero velocity. As we know, we later use this information to set our initial conditions for the model. We apply Newton's second law to construct a computer model to help us understand and predict the observed motion. In this case, the velocity is changing, meaning the velocity is non-zero. This implies that F net is also non-zero. There is at least one agent in the surroundings that is exerting an influence on the object. One of these is the force Earth exerts on the object, the weight force. We build a model based on this assumption. The ball's mass is 0.05 kilograms. The position and velocity are estimated from the video position from the origin, as stated before. We check the time step, delta t, to make sure it's small compared to the 0.766 second duration of the observation. Here it's set at 0.001 seconds, and that seems reasonable. We also need to provide initializations for the interactions being modeled. In our model for weight, I specified the constant g to describe the magnitude of the weight force. I also defined the axis unit vector, j hat, to describe the direction of the weight force. The 1 is in the second location of the vector because the eraser is only falling in the y direction. Here we have the calculation loop, which we use to do the actual motion prediction using Newton's second law repeatedly. This code predicts the new velocities and uses the velocity predictions to update the predicted positions. I also set the total time for making these positions to be consistent with the total observation time of the analyzed video motion, 0.766 seconds. Now we can run our model, VPython test model. This looks accurate, as well as the position versus time graph created. Now we can compare the model predictions in further detail by plotting them on the same graph as the experiment or observed positions. Here there are good predictions, but for a larger time, the model predicts the object to fall farther than what was observed. This suggests that the object's interaction is affected by another force, drag force. The drag force is the force opposing motion of direction due to air. In our code, the only difference is that we add drag force to F net, since F net is a total of all the forces. However, because we use B, we need to initialize it so the computer knows what we're talking about. So we know that B depends on the details of the airflow around the object, which depends on the properties of this object, like shape and size. In my code, I tested different values of B each time until the code was run, looking at the output window until the predicted final position was equal to or close to the predicted observed position. From this procedure, we can now figure out our B value, negative 0.03 Newton seconds per meters, which we can now use to initialize under our code for J hat. Basically, we've performed a fit to our drag force model by using our observed data. We also included arrows to represent force vectors. Here's the code for that. Now we can finally compare the predictions of our revised model with the original experiment data. When we run this revised computer model, as the object falls, the yellow arrow represents the weight force, while the blue upwards arrow opposing the direction of motion represents the drag force. The magnitude of the drag force depends on the object's speed. Since the eraser reaches terminal velocity pretty quickly, it makes sense that our drag force is quite similar to the magnitude of the weight force. To really compare the models, however, we need to plot them together. The weight force model and weight and drag force model both overestimate the eraser's position with smaller time. However, as time goes on, drag force becomes more significant and causes the weight and drag force model to line up with my observed data because air resistance is slowing the object down. The revised model doesn't really predict well either. We used a set of initial conditions from our observations to create it. Additionally, at the end, we fit the constant b of the drag model to fit the final observed position. Therefore, we look to the middle for the best predictions, but even this is not accurate. The perspective distortion might cause this as long as more force assumptions we could have included. Here are my questions, and here's a recap. Thank you.